Hello, if people are there. If you can tell me in the chat when you come, when you log. Anyway, I'm recording that to video and I hope that the bandwidth all is okay because it's nearly the first time I'm doing this Twitch thing. So if you have any feedback about it, I hope at least the recording will be available. The goal here, this is not a presentation at all. It's something I wanted to do for a long time, looking at Marcus Winand use the index Luke. So this website has a lot of recommendations and explanation about how indexes work in different databases. Marcus has also written a book about it, and this is available in many languages. And basically, what is really interesting there is that for all different points about indexes, there are examples for the most common databases, DB2, MySQL, Oracle, Postgres, SQL Server. And what I want to do here is run those examples on Yugabyte. YugabyteDB is Postgres compatible, so most of the code from the Postgres example should work without any change. However, the storage is distributed and the internal storage of tables and indexes is very different. For example, we don't use B trees like in all those databases. So my goal here is to go through the different chapters and see what is relevant or not, and what must be thought differently in Yugabyte or just use the same as in Postgres. And most of the examples are on an example schema. I will take the Postgres one because the Postgres DDL and DML is the same in Yugabyte for the simple reason that we reuse Postgres for the query layer, for the SQL layer. And I will start by creating the tables mentioned there. So I will copy paste all that in a file and we will run it. I made the fonts quite big because I'm not sure about the quality of the output in Twitch, but also in the recordings. So first, creating an employee table with a few columns. We have exactly the same data type as Postgres because we use Postgres. Next, there is a function. I will run the whole function creation. I do not expect any error with it. Okay. Next, some inserts with generate series. Some, yeah, I will run them one by one, but all this works in Yugabyte exactly the same as on Postgres. Last command, vacuum. This one works only for the compatibility, but we don't have vacuum in Yugabyte. We don't have these problems with the transaction ID wraparound. We don't have this problem with bloat. We have a different storage that has been designed to avoid all those problems. So the only thing we do when you run vacuum in Yugabyte is telling you that it's no operation, but we accept it just not to raise an error if you run scripts that you have built for Postgres. So I've run all the table and function creation from there. Just checking if there are other ones. We will do the other ones when checking the different chapters. Maybe, so if I want to look at my table exactly the same, I'm connected with pSQL exactly as Postgres. So if I describe employees, I should see the definition of it. And yeah, one small difference is that in Yugabyte, we shard automatically, which means we distribute the rows automatically to multiple nodes. The shards are called tablets, and the distribution is done automatically by default on the primary key with a hash function. With a hash function on the first column of the primary key. The default is hash on the first column, range on the others. And of course, we can mention another sharding method. This is only the default. And because I've run the Postgres code that doesn't mention any sharding method, because Postgres doesn't shard the tables, the default was there, but I can see it when describing the table, and we can also see that it is not a bit tree, it is a LSM tree, completely different storage. Still the same idea as any index. You store data sorted to be able to find a specific value or a range of value and get them ordered if you need to. But here we don't have a bit tree structure. We have LSM tree, which only happens the new change. So the big advantage of it versus B-tree is that we never update an existing block. We just append, and then there are some compactions going to different levels. Of course, the first level is in memory, and the next level go to SST files. But maybe we will see the more details about it when playing with indexes. I see nobody in the chat, so maybe just the streaming is not working. I will continue because I record that anyway. So this should work. And let me just check something. Yeah, I can check the table in the Yugabyte GUI. So here is the cluster I'm connected to, and if I look at the list of tables, I have other tables, but the one I've created is employees there, and I can see its structure, so the columns that I've created, and the tablets, hash sharding on the employee ID. So for some employee IDs go into this tablet, some other there, some other there. I have 3 tablets there, and they are replicated for high availability. They are replicated to the 3 nodes I have in my cluster, but each tablet has a leader in a different place. The leaders are distributed. So basically, the rows for these tablets have their leader on one node, the others on another node, and this is how it is distributed. Just checking one more thing. We have a list of indexes there, and I have no indexes, which may sound strange because I have a primary key, but that's the specificity. We don't use heap tables and B-trees. We store directly all rows into the primary key index, like clustered index in SQL Server, like InnoDB in MySQL. Okay, so going back to Marcus Winand website, I have my examples there, and then I can start to look at the different chapters. So the preface is explaining that the SQL language is declarative. So this is an example of query where you just declare what you want, the age for a specific employee, the date of birth. And I will focus only on what is specific to different databases, so going fast there. In the book or in this website, there are a lot of reference to B-tree because all the databases considered there have B-tree indexes. It's not our case with Yugabyte. We use LSM trees. So next chapter about anatomy of index. I will go fast on it because we use different indexes, except there is here a mention about clustered indexes in SQL Server or MySQL InnoDB that mentions that the table itself consists of the index structure. This also exists in Oracle with indexed organized table and is described in a later chapter. We are exactly in this case with Yugabyte. The table itself is stored within the primary key. So what's next? More about B-trees. So we don't have B-trees, we don't have leaf nodes, so I'm going fast on it. Those diagrams are not relevant. And the problem of clustering is not relevant. This is with B-trees and heap tables, where when you look at an index, you may have to read at random from different places into the table. The advantage of clustered indexes or LSM tree is that everything is already stored close to each other in the table as following the order of the primary key. This is again about the B-tree structure. We don't have branches, we have different levels. And some mentions about index scan. So we will see mostly the same. Those are the names in Oracle. Yugabyte has its roots in distributed databases, and distributed databases started with no SQL, like Cassandra, for example. And in NoSQL, we call that point query or range query. So in an index, we can go to a specific point, and if it's a primary key index, we will get only one row for a specific value. If we have more rows for a value because it's a secondary index that is not unique, or because we query only on a subset of columns, or because we query with an inequality or with a between, then we will have a range scan, but it's quite the same, just you read multiple entries. And this is special when there are heap tables, which is not our case, when the table is stored elsewhere, not in the primary key index. When you have the index entry and you need more information that is in the table, you need to go to the table. And especially in Postgres, you always go to the table. Even if you do an index-only scan, you have to go to the table at least to see the visibility. And now I think this is where we will start to see some examples, the where clause, because what Marcus Winand makes very clear there is that you index for different parts of your SQL query the where clause because you want to use it to filter, but also the order by, also the group by. So here we start with the where clause. And the where clause, the most simple is a where clause with an equality operator. So equality operator, and we will see some things about primary key, concatenated key, and slow indexes. Let's go next to it. So this starts with the simple table that we have created. Let me just check that we have created the constraint. Yeah, the constraint is the primary key, so this is created. So here Marcus mentions that the database automatically creates an index for the primary key. That's the case in all databases. And here, because the table itself is stored in the primary key, of course, the index has been created. The index, the primary key index is the table with Yugabyte. And the following query mentions that we use the index. What I will do, I will put the queries in the file to run them later. So this is a query that selects from, I don't know why. I thought that let me just close Slack because I don't want notifications during this Slack and task. Suppose this is the right way to close it. Perfect. So what I will do each time I run a query, I suppose that it's also mentioned in the website, but I will do that now. I will explain on it. Explain, I don't need the costs, especially because the costs in Yugabyte are still very not using all statistics yet. It's work in progress, but I want an explain analyze to see the execution statistics. So if I run that, I can see the execution plan for it, and I guess it is exactly what is displayed here. So for Postgres, we have an index scan. And because Yugabyte is compatible with Postgres, we show the same execution plan, even if it's a bit different. In Postgres, when you see index scan, it means that the filter, the index condition, will help to find the range in the index and then get entries and then get more columns from the table. And we can also see them if I explain verbose. I will see the output columns. So I need to output first name and last name, which are not in the primary key index there. So Postgres has to go to the table. With Yugabyte, we show the same execution plan, but because we store the table within the primary key, this doesn't have to read the table because we are already in the table. So it shows index scan, but on a primary key index, it is exactly the same as an index only scan. So something that is very, very fast, whatever the number of columns that you query. And maybe to see more about that, we don't have yet a lot of statistics, execution statistics in the execution plan, but we expose the statistics in JSON endpoint. Let me show them. If I go to the cluster, and I think that if I go to metrics, we have a lot of metrics that we expose there in a JSON endpoint, and I have a small tool to gather them and show them from SQL. I have this in a GitHub repository. This is the repository where I have my Docker files and some script to do some demos, and I have this that will gather some statistics. I will show you quickly how I do that. So it is a JSON endpoint on port 9000, and I use the copy statement from program to execute on the server a program. And because I want to be sure that the program is there on any situation, I use the bash/dev/tcp to query TCP port. I use a bit of awk to format it, and I send a get to do the HTTP thing without using curl in case curl is not installed, for example. And I do that for each server in YB servers. That's something that we expose in Yugabyte because we have multiple nodes, different from Postgres, where you are connected to an instance and your reads and writes go to this instance. Here we have multiple nodes. In this lab, I have 3 nodes, and YB server select star from YB server, show me the different nodes, and the nodes can be tagged to specific cloud regions. This is all for high availability and geo distribution. And basically, I have queries on it because this gets JSON, and then I use Postgres JSON functions. We have all them in Yugabyte just because we use Postgres for that. I will run this on my database. If I copy paste everything, which creates some tables, some views to be able to query. And I have basically 2 functions. One that is snap reset to reset the statistics I collect because statistics are cumulative. Execute. And I have a snap table that shows the most important statistic per table. Here I have no activity since the last reset, so I see nothing, of course. But I will put all that in my script file. And if I run that, I will see the same. So it executes the query, it shows the execution plan, and shows the 2 statistics I'm mostly interested in. I started to show that last Friday at YFTT talks. So in the LSM tree, so it's not a bit tree where we go through branches to leaves. In the LSM tree, we have basically 2 main operations. We can seek to a specific offset. That's the goal of an index, having things ordered so that you don't have to full scan from the beginning to the end. So seek, and then reading values. When you read values, you can read the next value. And if you need a value that is elsewhere, you can seek again. So basically, I want to see the number of seeks and the number of next, but especially the 6 gives a good idea about the different places where we go. So I have also, I will also run it per tablet first to explain better what we see. So I have here my table employees, and I can see that I have 2 tablets there on the same host that are concerned by my query. Now I check the table, and we have 3.6. Let's try to understand why I have a primary key. Actually, I expected only one tick there because I have a primary key going directly to the employee ID, which is the only column in the primary key. So I expected only one tick there, and then get the columns, which explain the 5. I don't know exactly why I have 3.6 there, but the idea is to show that with an index you can go quickly to one place if it was a full scan, and we can also see what would be a full scan with ints. We have PG implant enabled by default in Yugabyte. Scan, no, sex scan, employees. If I run that, I have a sequential scan there, and I can see that a sequential scan has to go to all tables with one tick because it has to go to the beginning of it, simply, but reading a lot of information from there. I don't know exactly why I have 3 there. There are maybe some lock information. I'm not completely sure. But basically, with an index, we are able to read just the small amount of data that we need rather than reading a lot and filtering them afterwards. So that's the big difference. The plan with an index can add my employee ID predicate as an index condition. With a second scan, it was a filter, and the filter is done later. Here, I can see that my query returns one row out of 1000, but most of the rows have been removed after the access, have been read to be filtered after. And because Yugabyte is a distributed database, we have those 2 layers. We have the Postgres layer, and we have the storage. And the 1,000 of rows had to be read from all nodes to be filtered later by the query layer. So indexing to get quickly only what you need is always a good idea in all databases, but it's more important in a distributed database, because if you are not in a distributed database, you probably read too much from memory. Here we are doing RPCs to different nodes. Okay, I'm just checking. I see nobody in the chat, and I supposed that the streaming doesn't work. I hope the recording works. If not, I will do it again another time. But let's continue reading what we have there in Marcus Winant book, online book. So yeah, it says that the Oracle plan explicitly to show that we go to the B tree and then to the heap table. Postgres doesn't show it, but you know that index scan in Postgres means that you have to go to the index and then the heap table. With SQL Server, this is probably not a heap table because we see the going to the index and then look up on the table. MySQL InnoDB stores everything in the primary key, and DB2 I think has heap tables. I'm not completely sure about that, but it seems to, yeah. But we don't really care. With Yugabyte, when you read from the primary key, you read only from the primary key, even if you need more columns just because they are there. And I think that was the point on this page. What if you have primary keys without a unique index? This is possible. I think it is possible also with Yugabyte, but the difference is that because we store the table within the index, it's much better to define the primary key in the create table statement. You still can create the table and then alter to add the primary key, but the create will store an internal primary key and then the alter will rewrite the whole table. So that's something, for example, that we do if I have a pgdump from Postgres. Usually you have the create table statement and then it loads data and then it adds the constraints like the primary key. Don't do that with Yugabyte, because if you create a table without a primary key and load data, then adding the primary key will have to move the whole data again. So much better to create the primary key when the table is empty, and much better to do that directly in the create table statement. We have with Yugabyte, we have a fork of pgdump that does those things that are more optimized with that. Okay, now about concatenated index. So I will check the example schema. We will see if this works on those tables. So for the demonstration, let's assume that there is a company merger and the employee ID is not unique across both companies. And then we need to extend the primary key by an extra identifier. So the new primary key has two columns, employee ID, subsidiary ID. So we will see how it works on Yugabyte. As I mentioned, because we store the table in the primary key, changing the primary key is something that has to do more work. You should know your access patterns for the primary key upfront. So we need a new column, and I suppose that this is in the example schema for Postgres. We have seen the where clause, so this is what we have run before. And about the concatenated keys, I have to add this column to show the example. So this works. Adding a column, of course you can do it. Updating to put some data into it. And setting it as not null. Okay. Oh, I see that Pete is in the chat. So streaming works fine, and thanks a lot for the feedback, because I had some doubts. I started it on my phone to see if it was working, but it was not. But I think it was more a problem of 4G. Interesting. So in Yugabyte, is it advised to have a primary key definition inside the create table? Yeah, it is. And maybe I will do that now, just to answer Pete's question. Let's say that I create a table demo without a primary key, so A int, B int. And I will put some data in it, insert into demo, select G rate series 1, 10, I don't need a lot, and 42 for the second one. So running the insert, running a select on it, and let's describe it. I see that I don't have a primary key, but internally we have a primary key that is generated with a UID, which I cannot query, but it will be used, for example, if I create a secondary index, create index demo b on demo b. A secondary index must need to address the table rows. And for example, in Oracle, we have a row ID for it. In heap tables, we have a physical ID for it. For tables that are stored in the primary key index, we cannot have a physical address because they can move in the index structure. So there is an internal ID used by it. What I wanted to show is that I can alter table. Yeah, just check. I was just checking. I have unique numbers in A, so alter table demo add primary key A. And this, so I have only 10 rows there, but this is a reorganization. It creates a new table. It is online, but it creates a new table to move data to it later. And I have the primary key now, and I still have my index from before that is still usable. So that means also that this index has been reorganized to address it differently. Maybe I can run the same and checking the statistics drop table demo. So I will insert more rows, 1000. So checking, I have no primary key there. And yeah, I will create the index also. And I will call execute snap reset before, snap reset before running the alter table, and then look at the statistics since the snap reset. So snap table. Not a really good demo because I expected to see things there. Yeah. When I take the snapshot of the statistics, it stores them with the tablet unique ID, and I think they have changed, so cannot throw it. What I wanted to say is that we have read the old tablet and rebuilt the new tablet for the table. It is a reorganization, but it's not easy to see it because the IDs have changed. So to answer clearly, it is much better to put the primary key definition within the table, and also to think about the default that is hashing on the first column, which is in many cases a good idea, but it is not if it's something where you may want to query by range. And then you can also define when you create the table, by default, many tablets will be created depending on the number of nodes you have, but you can also split them later or have auto splitting later. But when you create the table and you know that you will have a lot of data, for example, you can create it and mention how many tablets with a split into. And the same with indexes. You mention the number of splits. Okay, now going back to the example we wanted to see with, I think we added a colon, or did we? Checking what I wanted to do is adding a colon there. Maybe I didn't do that. Yeah, I didn't do that. So I will just go at the end, put that in my file if I need to run it again. And the idea there is to change the primary key. So drop the old one and create the new one. And this, I don't think is something that we can currently do, but I will check. So dropping the primary key is not supported in Yugabyte because dropping the primary key means reorganizing it, and then of course changing the primary key is not possible. So if we want to do this exercise, we will clearly create the new table and move data to it. I will simply create the table with this new column. So drop table employees. And what we want is subsidiary ID in the primary key, and this is where I will think about it. I identify employees with the subsidiary ID and the employee ID within the subsidiary ID. How do I want to distribute that? Maybe I have a lot of subsidiaries and then hash on it and distribute the employee ID by range. Or if I have only two subsidiaries, it's not a good idea to hash on it to have only two values. So keeping employee ID first is probably a good idea. I will add hash to both of them, where my idea is to distribute employees ID with their subsidiary ID. And I need to add the colon. So where was the colon? Definition, subsidiary ID as numeric and not null. Not null for a primary key makes sense. Okay, let's check the creation, the drop and the creation of the table. Multiple hash colon must be defined. Yeah. If I want multiple hash colons in Yugabyte, I will define them like this. So we are Postgres compatible, but of course there are some addition because we have this distribution in addition to it. So you can use Postgres code and you can customize it to give more information about the distribution. So here I have created the table. I need to generate data, and this function is still there. I did not remove it. The insert is still the same, except that I have a subsidiary ID of 30. Okay, so subsidiary ID, and that's 30. So here, instead of doing alter tables and update, I've recreated the table as it would have been after those statements there with the primary key. And now inserting more data, I think here we insert more data just to show, have some duplicates among the different subsidiaries. So now I'm going at the end of my file and inserting those rows. No need to vacuum because we are on Yugabyte. And then we will be able to do those exercises with the subsidiary ID. So the new primary key is just extended. New records are randomly assigned to 29 subsidiaries. Yeah, so 29 subsidiaries can make sense to hash on subsidiary and maybe range on employee ID if we want it. Here we hashed everything. And I think this was what we needed for this query. So showing what happens. A query for a particular employee has to take the full primary key. So yeah. Important. Now, if I have a query with the full primary key, and I will do the same as before, doing explain plan for them. I will take those and I will show the table statistics as well. But most important, execution plan and index scan. So very similar to what we had before. We have a full predicate on all primary key columns, which means that I get one row directly from the index by seeking at the right place and reading information from there. This is the table, but the primary key, there is no need to read anything else. So that's also very important in the distributed database. The loops between indexes and tables would be more expensive than in a monolithic database, and this is also why we don't have indexes plus heap tables for this. This shouldn't scale in a distributed database. So what are Marcus Winand remarks on that? We use the complete primary key. So it can use index unique scan. This is the name in Oracle, but here index scan on primary key is the same. And now an interesting one. What if we query all employees for one subsidiary? And I will put that also in sorry. Yeah, I will put that. So I will reset the statistics and explain for this query. I don't think I've run explain. Yeah. So reset the statistics, explain. And here I have a sequential scan. I will check if this is what, yeah, this is what was mentioned there. Here I have a full scan. So the idea here is that we are reading all employees for a specific subsidiary. We have, let me check how many records we have in this table. Select count star from employees. We have 10,000 employees in this table. And here we have read most of the 10,000, but discarded because of this filter to get only 39 rows. Now, the question for the optimizer for the query planner, is it better to do a full scan to get that? So to get out of 10,000, to get 39 rows out of 10,000 ones. In Postgres or Oracle with heap tables, probably it's better to do a full scan because reading 40 rows through indexes would mean, especially if they are randomly distributed into the table, would mean a lot of additional gates. With Yugabyte, I think that it would be better to read from the range, from a range of subsidiary. And while saying it, now I know exactly why the query planner didn't use that. What I wanted to get was the range of subsidiary ID and then read everything. But this is not possible with the current index because we have created employee. We have created with employees with the subsidiary ID at the end. That's one thing, and hashed. So with this kind of structure, I hashed the employee IDs into 3 tablets. I have 3 tablets there, and their employees' ID are grouped by their hash value and then by employee ID. So people from the same subsidiary are scattered everywhere. And I think maybe that's what is mentioned later in the use the index look website, but I will do that myself. I will, if I know that in my access pattern I have some queries that read for a specific subsidiary, then I will put the subsidiary first. And that's interesting because many people say that it's better to put the more selective column first, but this is overlooking many other things. For example, this one. I will recreate the table with a different primary key decoration. So I put that in comments, put it in the way I think it is the best schema for those kinds of queries. So first, the subsidiary. I don't expect range scans like give me subsidiary between 10 and 12. So I hash them. And we have 20 subsidiaries, and then I want them to be distributed in different nodes. But then for one subsidiary, I will put together the employees and with a range. It's the default. I will say ascending. I may not need it, but because I've already distributed enough, in my opinion, with subsidiary, I don't need to distribute the employee IDs. So in case there are some queries, for example, looking at the 10 first employee IDs, it would be possible. So I will create this table in this way and insert all the rows as before. The function didn't change. The insert here of 1000 of rows, and I think I add another insert to put the subsidiaries. Generate more records. Yeah, this one. Okay, so I have the same data as before, but with a different primary key. Of course, this has a cost, and this is why when you design your database, you should know upfront the main access pattern. We are talking about the primary key, and this concerns the main access pattern. If you add new use case, you will be able to create more indexes, but the primary key, that's an important one. So what do I have? If I run the same query, give me subsidiary 20, all employees for subsidiary 20. I don't know exactly. I had 39. Oh, yeah. There are some random generations. So before I had 39, here I have 42. But it's the same idea. But here, we didn't have a sequential scan. Here, we have been using index scan. So this is a range because we have read many rows from there, but all those rows were close to each other because when looking for subsidiary 20, subsidiary being hashed, what Yugabyte does is calculating the hash code from it and then go directly to the right tablet. My table is onto 3 nodes, but for this specific hash code, I need to go to only one, and then from there, read contiguous values. So because you see multiple 6, you may think that they are not at the same place. It looks like it had to go to different offsets. The point is that there is an optimization where if you need to read multiple values with a next, then it's faster to do a seek, but a short distance seek. So this is why we see multiple seeks, because in the LSM tree, all data is stored with documents, but a document for each row, but subdocuments for each column value. So when I query a structure with multiple values, I have to read all values. So I could have done, Yugabyte could have done that with only one seek to the specific place and then reading next, but because I need only 2 columns there, probably there are some optimization where there are small hops, but they are close together, and close together means that probably in cache when you read them and not scattered IOs. So that's the thing I've done, and I see that it's nearly 1 hour. I will do other tweets session. My goal is to cover the whole this whole website with all examples and go slowly. And if there are questions, then that's perfect. So I will stop after that, just looking at what was the comment there. So for this query reading for subsidiary, the execution plan reveals a full scan. This is what we had because of the definition of the primary key, because subsidiary was not first. And I optimized that, putting it first, and probably that's what is done later. So concatenated index, we have here a concatenated index with 2 columns. And the idea is that it's easy to get at the right place for the first column. If I have a predicate on the second column, then the value for the second column can be a different place. And we will probably see in next sessions that there are some optimizations like skip scan where we can still do queries on the second column for any value of the first one, but the most optimal is really to find directly the right place in the index and read a range from that. this is exactly what, so what we did is exactly what Marcus Winant says here. We can take advantage of the fact that the first index column is always usable for searching, and then the recommendation for a data model which must be optimized for this kind of query on subsidiary only is to have subsidiary first. I did more with hashing here on Postgres or Oracle or all those monolithic databases. You don't care about hashing because they all go at the same place, but it's the same idea. Put that first, and then the execution plan. So the Postgres one will, could be the same as what we have seen with index scan. But that's important, and I will go a bit over the hour that I've planned before, because this is really important. You see a big difference there between the plan in Postgres and the plan in Yugabyte. Bitmap index scan looks really cool, because what Postgres does here is read from the index, and rather than going for each entry to the table, which has a cost, better get all entries and go to the table later. But we don't need that in Yugabyte, because we don't have to go to the table. If we seek into the primary key index, we are already in the table, and we just have to read the column values from there. In Postgres, like in Oracle, like in SQL Server, if you don't use clustered index, and like in DBU, reading by index, even if it's a primary key index, is exactly like a nested loop. It's like a join between the index and the table. And this is why Postgres has to optimize it. And the bitmap is not because instead of storing the list of the entries to go to the table, it's just builds a bitmap of the pages of the block that it has to visit. And the idea is that sometimes with an index, we are reading the index and we reference different places in the table. And sometimes we have to go back. The next value in the index goes to a block that we already have visited. So this kind of plan in Postgres helps to visit only once each page. But in Yugabyte, we don't need it because we don't have heap tables. And anyway, we don't have pages. Pages, blocks, is the structure that is used in those monolithic databases. And mostly because they started when data was stored on mechanical hard drives with a high latency, and then you prefer, you will not go to the disk just to read a few small values. You prefer to read a whole page and keeping in cache, so a buffer that you keep in buffer cache. And then if you have to revisit it, or if you have to read many rows from it, it is already in memory. And that's really good. And this is also what makes B-tree efficient. B-tree would not be efficient if they had to go to disk, because with B-tree, especially the maintenance, has to go to update the blocks. If it's in memory, it's easier. Today, most of the databases, if you want some performance, especially for OLTP, most of them will be on SSD. With Yugabyte, we support only SSD. The goal is OLTP and a small latency disk, as we can have today, as we can have on the cloud. So there is not this need to deal with data with blocks, buffer to reduce the latency. That's one thing. So sounds cool. We don't need it because on SSD we don't need that. But the other thing is that more than we don't need it, we just cannot use shared buffer in a distributed database. Because shared buffer, that's easy if all your sessions are on the same node, because you put the shared buffer in memory. But if your sessions can be connected to many nodes, so many servers, you cannot share the buffers between them. Or with very specific things like very fast network, for example, a vehicle rack shares the buffers in some kind with the global cache, but the buffers, the current buffer moves from one node to the other, and this has a latency, which is okay if your nodes are really close, but you cannot do that, for example, when you distribute to multiple regions. So that's one thing that is very different, and that also justifies that we do not use bit trees. Bit trees are okay only if you have shared buffer. You cannot use bit trees in a distributed database. And we also don't need it as much as the old databases needed to overcome the latency of mechanical disks. With SSD, we can do some random reads without latency. The only thing is the writes, where you prefer to write large amount, because writing on SSD may have to rewrite a whole page on SSD. And the LSM3 is really good for that, because you just append things in memory and then you write them as a whole. So I went a bit further from what I wanted to do on this page, but this is very important to mention. If you move from Postgres to Yugabyte, you will not see those bitmap operation, and in many cases, just because you don't need it, this index scan, which is actually the same as an index only scan on the primary key, is the fastest you can do to get the range from the specific structure. So for this, the index scan is faster than the bitmap it scan. There are some cases where you may have plans that are good enough with bitmaps, and you will not have the same in Yugabyte. You will have to think about the indexes. When you see that, this is a workaround for a bad clustering factor between the indexes, bad correlation. But yeah, so different plans, but same idea. If you start from the index, if you start with the first column, then you can go directly to the right range. Okay, if people are still there, questions in the chat, but I will put also this video on YouTube if the recording is okay. And so on YouTube, search for my name, Frank Pachot, you will find it. I have also a blog. I blog on the Yugabyte blog. I blog also on Dev2. You can send me emails. And so you have everything at on the screen there. And Twitter, I use a lot Twitter. So if you have questions, anything about indexes, you can do that. And one more thing, at Yugabyte, we are doing the FTT, so Yugabyte Friday Tech Talks on Friday, nearly the same time as we are now, because it's yeah, it's nearly the same time. We have changed the daylight saving, so I don't remember exactly when it is, but just follow on LinkedIn or Twitter and you will see it. Last Friday, I did something about indexes and we had a lot of questions, so I will do more, maybe not next week, but the week after that. And I will try to do those Twitch every week at the same time. I hope it is okay for most of the people. Anyway, it will be recorded. Maybe not all weeks, because physical conferences are starting now. So better to meet in person rather than remotely like this. And next time I will, let me just put the URL in my file so that I know exactly where we are on the next time. And I will do the same, taking, so this is really a recommendation, the website from Marcus Renand, but also the book, which is referenced somewhere. Yeah, the book that is also in different languages, French, Japanese, German. So this is just perfect if you are a developer, if you are a DBA and want to understand or talk indexing with the developers. This is a must. For Yugabyte, there are some things that are different, and this is exactly what I'm doing with those tweets. Maybe I will write something later. We will see. Okay, so I will close this in a minute. Do not hesitate to give me some feedback. I hope the recording is okay. I'm quite new with Twitch and OBS, and this is using a lot of CPU on my laptop. So thank you very much, and see you next time. I think I will do it next week at the same time.